Quantum computing represents a fundamental shift in how we think about computation. Instead of relying on classical bits, which are restricted to binary states, either 0 or 1, quantum computers use quantum bits, or qubits, which can exist in a superposition of both 0 and 1 at the same time. This property, rooted in quantum mechanics, gives quantum computers the potential to process information in ways that classical computers never could. To understand quantum computing, we must first explore the bizarre but powerful principles that come from quantum physics. At the heart of quantum computing lies the principle of superposition. In classical computing, a bit can be in one of two states, 0 or 1. But a qubit, thanks to quantum mechanics, can be in a linear combination of both 0 and 1 simultaneously. Mathematically, a qubit state is represented as psi as A0 plus V1 1, where A and V are complex numbers, and the probabilities of observing either 0 or 1 are given by I2 and AV2, respectively. This allows quantum computers to represent multiple states at once, drastically increasing their computational power for certain tasks. Another critical concept is entanglement. When two qubits become entangled, the state of one qubit is intrinsically linked to the state of the other, regardless of the physical distance between them. If one qubit is measured, the outcome immediately determines the state of the other. This non-local correlation cannot be explained by classical physics, and is what Einstein famously referred to as spooky action at a distance. In a quantum computer, entanglement is used to encode relationships between qubits that allow for sophisticated parallel computations and quantum error correction. Interference is also a vital ingredient in quantum computing. In the quantum world, probability amplitudes can interfere constructively or destructively, much like waves, leading to the amplification of correct outcomes and the cancellation of incorrect ones. Quantum algorithms are carefully designed to leverage interference so that, after running a computation, the correct answer is much more likely to be observed upon measurement. This subtle art of manipulating interference is what allows certain quantum algorithms to outperform their classical counterparts. To control qubits and implement algorithms, quantum computers use quantum gates. Unlike classical logic gates like AND, OR, and NOT, quantum gates operate on qubits through unitary transformations, which preserve the total probability. These include gates like the Hadamard gate, which creates superpositions, the Pauli gates, X, Y, Z, and the CNOT gate, which enables entanglement. These gates are combined into quantum circuits, just as classical gates form digital circuits. A quantum circuit is a series of gate operations on a set of qubits, leading to a final measurement that yields classical information. Unlike classical computing, quantum gate operations must be reversible and deterministic in the sense of linear evolution. This reversibility arises from the fact that unitary transformations are inherently invertible. Quantum circuits can simulate classical logic but also go far beyond it, especially when leveraging entanglement and superposition. In essence, the power of a quantum computer grows exponentially with the number of qubits because it can process all possible input combinations simultaneously. Quantum computers are not just theoretical curiosities, they are being built and tested today. Companies like IBM, Google, IonQ, and Rigetti are developing quantum hardware using various technologies. The most prominent among these are superconducting qubits, which use cryogenically cooled circuits to maintain coherence, trapped ion qubits, which use electromagnetic fields to trap and manipulate charged atoms, and photonic qubits, which use light particles to encode information. Each platform has strengths and weaknesses in terms of coherence time, gate fidelity, and scalability. We are currently in the NISQ era, short for Noisy Intermediate-Scale Quantum Computing. This refers to quantum devices with dozens to hundreds of qubits, which are not yet capable of full error correction, but can still perform interesting computations. These devices are susceptible to noise, decoherence, and gate errors, but researchers are actively developing quantum error correction codes and fault-tolerant architectures to build larger, more reliable systems. Quantum error correction is a cornerstone of long-term quantum computing. Unlike classical errors, which can be corrected by copying bits and performing majority voting, quantum information cannot be cloned due to the no-cloning theorem. Instead, error correction relies on encoding logical qubits into entangled states of multiple physical qubits. Techniques like the Shor code, Steen code, and surface codes are designed to detect and correct both bit flip and phase flip errors without violating the fundamental rules of quantum mechanics. The real promise of quantum computing lies in its algorithms. One of the most famous is Shor's algorithm, which factors large integers exponentially faster than any known classical algorithm. This has major implications for cryptography, as many encryption systems, such as RSA, rely on the difficulty of factoring large numbers. If a fault-tolerant quantum computer is built, it could break RSA encryption, prompting the need for post-quantum cryptography, classical cryptographic systems that are resistant to quantum attacks. Another well-known quantum algorithm is Grover's algorithm, which provides a quadratic speedup for unstructured search problems. If you need to search through a list of n items to find a match, a classical computer would take O(n) time, but Grover's algorithm can do it in O(n) steps. While not exponential, this speedup can be significant for large datasets and has potential applications in optimization, machine learning, and beyond. In chemistry and physics, quantum computers offer transformative potential. The behavior of molecules and materials is governed by quantum mechanics, but simulating these systems on classical computers becomes intractable as complexity grows. Quantum simulation was one of the original motivations for quantum computing. Algorithms like the variational quantum eigensolver, VQE, and quantum phase estimation, QPE, can find ground state energies of molecules, enabling breakthroughs in drug discovery, battery design, and materials science. These hybrid algorithms, like VQE and quantum approximate optimization algorithm, QAOA, combine classical optimization with quantum subroutines. They are designed to work within the constraints of NISQ devices. The quantum part prepares a parameterized state, and a classical optimizer adjusts parameters to minimize a cost function. This iterative process enables useful computations even on imperfect hardware, and serves as a bridge between today's limited machines and the full potential of future fault-tolerant quantum computers. Developing software for quantum computers requires new programming paradigms. Languages like Qiskit, developed by IBM, Cirq by Google, PennyLane, and Bracket by Amazon, provide toolkits to write, simulate, and run quantum circuits. These platforms abstract away the hardware details and allow developers to build applications in chemistry, machine learning, optimization, and cryptography. Simulators are also available for testing circuits before deploying them to real quantum devices. Quantum machine learning, QML, is an emerging field that explores how quantum algorithms can enhance classical AI and ML techniques. While early research shows potential in using quantum feature spaces, kernel methods, and speedups for certain types of learning tasks, most QML algorithms remain theoretical or tested only on simulators due to hardware limitations. Still, the intersection of quantum and AI holds promise, especially as hybrid models evolve. Another important area is quantum networking, which involves sending qubits between distant quantum systems to create a quantum internet. Using entanglement and quantum teleportation, such networks could enable ultra-secure communication via quantum key distribution, QKD, and distributed quantum computing. QKD is already used in specialized applications for high-security communication, and satellite-based experiments by China and other nations have demonstrated early stages of quantum networking on a global scale. While the field is still young, governments and corporations are investing heavily in quantum technologies. The U.S. National Quantum Initiative, the European Quantum Flagship, and quantum moonshots in China and Canada are accelerating research and workforce development. Startups and academic labs are also thriving in the space, building tools, algorithms, hardware, and education platforms. Despite the hype, it's crucial to acknowledge what quantum computing cannot do. It won't replace classical computers for everyday tasks like browsing the internet or running spreadsheets. It's not magic. It's a highly specialized tool that excels at certain types of problems, particularly those involving massive parallelism, optimization landscapes, or quantum systems themselves. The true value of quantum computing lies in its complementarity to classical systems, forming part of a new computing paradigm. Getting started in quantum computing doesn't require a PhD in physics. Many entry points now exist for software engineers, data scientists, and product managers. If you're comfortable with linear algebra and basic Python programming, you can start writing quantum circuits using Qiskit or Cirq. Courses, tutorials, and simulators are freely available, and educational tools are becoming increasingly user-friendly. To navigate the quantum ecosystem, it's helpful to understand the stack. At the bottom is the quantum hardware, e.g., superconducting circuits, above which lies quantum firmware that translates gate operations into physical pulses. Above that are compilers, middleware, and programming libraries. At the top layer are applications where industry-specific problems are addressed, often using hybrid classical quantum approaches. The entire stack is evolving rapidly, and interdisciplinary skills are in high demand. The future of quantum computing is bright but uncertain. Optimists believe we'll reach quantum advantage, where quantum computers outperform classical ones on real-world tasks, within the decade. Skeptics warn that hardware and error correction challenges may slow progress. The truth is likely somewhere in between. Regardless, the field will generate value through its research, new math, educational programs, and spin-off technologies, even before universal quantum computers are fully realized. In conclusion, quantum computing is a field built on the counterintuitive rules of quantum mechanics, yet it promises to solve real-world problems that stump classical systems. From breaking encryption to simulating molecules and optimizing supply chains, its potential is vast. But realizing that potential requires not just breakthroughs in physics and engineering, but also a community of informed, curious, and collaborative learners. Whether you're a student, a developer, or a business leader, now is the time to explore this frontier and help shape the quantum future.